So let's talk about drone thermography. It's this incredible technology that lets us see a hidden world of heat all around us. But here's the thing, and this is really the key to everything. What you see in those colorful images isn't always what you get. The real story is a fascinating mix of physics, timing, and some serious detective work.
Take a look at this, right here. Is that glowing spot a sign of a catastrophic roof leak, one that's been silently wrecking this building for months? Or is it just a harmless reflection of the sky on a metal vent? I mean, get this wrong and you're talking about a massive, unnecessary repair bill, a financial disaster. The answer? Well, it's hidden in the invisible physics of what's really going on.
Okay, so let's get right into the most important concept you have to understand. A thermal camera does not see temperature. I'm going to say that again. It doesn't see temperature, it sees energy. And that one little distinction, that changes everything.
What's really happening is the drone sensor is getting hit with this cocktail of radiant energy. It's a mix of what the object itself is emitting, what it's reflecting from its surroundings, like the sky or other buildings, and even how the atmosphere between the drone and the target messes with that signal. All of that gets mashed together into what we call an apparent temperature. A thermographer's real job is to untangle that mess to find out what's actually happening.
So, how does this work in the real world? Let's take our first case. We're hunting for hidden moisture in a big commercial roof. Now, for a job like this, timing isn't just about, when it's convenient to fly. Now, timing is everything. It's dictated by physics. You fly at the wrong time of day, and your entire mission might be completely worthless.
The secret here is a cool concept called thermal inertia. Just think about it like this. Dry insulation is kind of like a small pebble sitting in the sun. It heats up super fast, and the second the sun goes down, poof, it's cool again. But insulation that's soaked with water, that's like a giant stone. It takes all day to soak up the sun's heat, and it holds on to that heat for hours after sunset. So we're not really looking for water, we're looking for the thermal signature of that giant slow-to-cool stone.
And this whole thing is a race against time. If you fly at midday, forget it. The sun's energy just blasts the roof and creates what we call a thermal mask, hiding everything. But wait until just after sunset, and you hit this perfect golden hour. The dry roof cools off fast, but those wet spots, our stones, are still glowing warm. The contrast is perfect. But if you wait too long, like until just before dawn, everything cools down to the same temperature, and all that evidence just vanishes. And there's another invisible force you have to worry about, the wind. Get this, according to the official industry standard, if the wind is blowing any faster than 15 miles per hour, your inspection is basically invalid. Why? Well, the wind acts like a giant fan, cooling everything down at the same rate. It's a process called forced convection, and it literally erases those subtle temperature differences you're desperately trying to find. Your evidence gets blown away. All right, let's switch gears. For our second case, we're looking at a building's walls. Now, this is a whole different ballgame, because you've got this complex mix of materials. And here, the biggest enemy isn't timing, it's the fact that shiny surfaces can and will lie to you.
So to understand this, you absolutely have to know about a property called emissivity. It's basically a score from 0 to 1 that tells you how well something radiates its own heat. Materials like concrete or paint have high emissivity. Think of them as loud talkers. They're shouting their thermal energy, so what your camera sees is really close to their true temperature. But then you have things like polished metal or glass. They have low emissivity. They're like perfect mirrors. They're terrible at emitting their own heat, so what you see is almost entirely a reflection of something else. That shiny metal vent might look freezing cold, but you're probably just seeing a reflection of the cold night sky.
And it all comes down to this one simple, super powerful equation. For any solid surface, emissivity plus reflectivity always equals 1. It's a zero-sum game. If something is a bad emitter, it has to be a good reflector. That's it. That is the fundamental rule that explains why shiny things can be so deceptive to a thermal camera.
Now, once you know how to deal with reflections, you can start hunting for real heat loss. And there are two main types you're looking for. The first is called conduction, or a thermal bridge. This is heat moving straight through a solid object, like a metal beam inside a wall. Its signature is sharp, it's static, it looks like a well-defined line. The second is convection, an air leak. This is heat being carried by moving air, like a draft. Its signature looks totally different. It's fuzzy, feathered, kind of like a plume of smoke. If you mistake one for the other, you're going to order a very expensive and very wrong repair.
And just like the wind rule for roofs, there's another hard and fast rule for finding these air leaks. The standard says you need at least a 3-degree Fahrenheit temperature difference between the inside and the outside of the building. If you don't have that, there's just not enough energy moving through that leak to create a signature your camera can see. The physics just isn't on your side.
Okay, so we've seen how timing, materials, and the weather can completely change the story an image tells us. So let's boil all this down into a set of golden rules, the things that turn a pretty picture into a real, defensible diagnosis you can take to the bank.
First, let's talk about the classic, most costly mistakes. The #1 blunder is just leaving the emissivity setting on the default of 0.95 for everything. That's a total disaster on a modern building with tons of metal and glass. Then, of course, scanning at midday, ignoring high winds. Another one is scanning a wet wall, because the evaporating water creates false cold spots. And maybe the simplest mistake of all, forgetting to take a regular photo. Without that visual context, that hotspot you see could be a huge problem, or it could just be a normal heating vent.
So, how do you get it right? It's really a simple 3-step process. First, you have to measure your environment, get the wind speed, the humidity, and the reflected apparent temperature. That's the temperature of whatever your target might be reflecting. Second, you manually punch those numbers and the correct emissivity for your target material right into your camera. Don't let the camera guess. And third, you fly at the right time, when the physics is working for you, not against you.
And this table just lays it all out, clear as day. This is the difference between good enough data and great data. The casual approach, it assumes everything. The numbers are just guesses. But a professional, defensible survey, every single variable is measured and recorded. This isn't just a pretty picture anymore. This is evidence.
Okay, so let's bring it all home. We've peeled back all these layers of physics and procedures and best practices. So what's the big takeaway here? What does all this really mean for you?
Here it is, the bottom line. A thermal image is not a photograph of temperature. It's a complex, delicate map of invisible energy. It's telling a story in the language of physics, a language of emissivity and inertia and convection. And if you don't understand that language, you're just looking at colors. You're just guessing. The image itself doesn't give you the answers. It just gives you the clues. So the next time you see one of these vibrant, colorful thermal images, I want you to just pause for a second. Ask yourself, what's really going on here? Will you just see a pretty picture with some hot and cold spots? Or will you see it for what it truly is, a fascinating puzzle of invisible physics, just waiting for someone like you to solve it?